Hello, in this video I'm going to be covering the principle of probability density functions. I should make it clear we are talking about dealing with continuous data here. So whilst we've seen discrete distributions with certain formulae or probability functions, with continuous data we are talking about probability density functions here, and we're going to cover this. And we're going to just talk about how what is a PDF. What are the conditions for a PDF, and we're going to work out probabilities using a PDF. And very finally, through one of the examples, we're going to talk about the mode of a PDF. Before I really get into the theory of this, because it's quite pure, it's basically the pure mathematical theory behind probability density functions. It's probably important to really appreciate the idea that we're modeling here. We're modeling continuous data, and it's probably good to refer back to histograms or even relative frequency density histograms, where basically you look at it's the area underneath with a relative frequency density histogram, which gives you the proportion of data that lies between two values. Now these histograms here are actual histograms which are taken from the OCRA data set for single maths about age distributions, I think in the 2011 census. And what I've done is actually through GeoGebra I've done two different histograms with different class intervals, and as you can say with this one, Portsmouth one, we've got more with this one here we've got more class intervals than with this one. And what I want you to imagine if I was to make even more class intervals. In other words, I was to split this into this one here into various little bits. It might go like that, mightn't it? Because it's unlikely to be totally flat. So imagine I was just to almost reduce this to infinitely small number of histograms, number of class intervals. I'm kind of going to end up with a curve, and that's our probability model. Now what the equation of that curve, well, it looks a little bit complicated, but we could perhaps model it by some mathematical function for that population of Portsmouth. Notice, just to go back to the actual data, they'll say this is actual data. We've got, and this one's a more crude measure because we've got fewer class intervals, but we've got a peak around 2030, which is probably to do with the university population here in Portsmouth, and Havant, just a few miles up the road. It's a very different kind of thing going on here, and it almost looks straight along. Might go wobble a bit, but it could almost be modelled by a uniform distribution until perhaps we got to around about here, and it might go down kind of linearly like that. So we could define it by some piecewise function. But the important thing here is that the area for a relative frequency diagram, because what we've done here, I think the population of Portsmouth is around about 200,000, so we've been divided by 200,000 so that the area underneath this thing is 1. And the same with the Havant one. The area of the population of Havant is around 120,000, I believe. And so whilst working out the frequency density, the relative frequency density, we've divided by that 120,000, and we've got an area of 1, which is why we've got similar numbers on the vertical axis with these, because the age, obviously it's fairly, the horizontal axis is varying from 0 to 105 approximately. So that the fact that we've used a relative figure means that we've taken out the fact that the population of Portsmouth is more than Havant, and we've then basically made it so that the area underneath this histogram is 1. And I say, if we were to do infinitesimally small class intervals, we might end up with this thing called a probability density function. So that's the kind of background of this. We're trying to model curves, if you like, or functions to actual distributions. Okay, and it's a very useful thing to be able to do. So now I'm going to talk about the pure maths now. Say, for example, this one here, we could say model that by a piecewise function. Say I'm struggling to come up with an actual function for this one, but the one thing they have in common is the area equals 1. So we're going to talk about the pure maths of this now, and what constitutes a probability density function. What are the important features to make it a possible probability density function? So let's go on to that now. So as I say, the important feature of a probability density function is that the area underneath represents the probability. Let's write that properly here. So the area underneath represents the probability of something occurring between those two values. With continuous random variables, we should always be talking about the probability that the value is within a range. As I said in one of the previous videos, the probability of it actually going bang on a value is 0, theoretically. So we're always talking about the probability, and basically what we want is the probability of something happening, or proportion of number of people or whatever to be lying within, involving the area in between two limits. So and that's totally analogous to the histogram. If we wanted to know the proportion of people in this place of Havant here, we'd find the area under there if it's a relative frequency histogram. Okay, so right, what other important features have we got? Well, of course it's got to be positive. So the properties of a, let's write that down, properties of a PDF. We need to first of all, it needs to be positive. You can't have negative area in this context, or negative probability, or negative proportion. So let's call our probability density function fx. So one of the important properties is that fx has got to be greater than or equal to 0. Okay. Right, now the next thing is the thing I've actually said, is that the probability or proportion of function of values between A and B are given by the integral of that function, because that's how we find the area in pure mathematics, isn't it? The integral. Okay, but it is the area. So in the first examples I'm going to do, don't use integration, because frankly, if you're finding the area of a rectangle or a triangle, it's better to actually use just more basic stuff. But yeah, in general, if we integrate between two limits, and for a probability density function to be viable, the integral has got to represent a probability somehow in that way. Right, and probably the most important thing of all is related to what I said about the relative frequency diagram, and that is that the total area is equal to 1. Right, now I'm going to do something a little bit pure mathematical here. I'm going to call it infinity to minus infinity. Now, in many cases, we don't go to infinity, but all the actual total area going from infinity to minus infinity equals 1. But don't worry too much about the infinity minus infinity. What you'll see is, a probability density function might be, might look like this, flat. So it's 0 for, it might go from here 1, and then it might go up to 2, and then 4, 5 or so, and then it's 0 for all other values. So really, with this particular function, it's only the values 1 and 5, which between 1 and 5 we'll be interested in. But in a pure mathematical sense, we can talk about the total area from infinity to minus infinity is equal to 1. And when we do the normal distribution, we'll see that this infinity to minus infinity is kind of relevant, because theoretically, the normal distribution curve looks has asymptotes, so it kind of never gets to 0. It does to all practical purposes, it does, but hopefully you get my meaning from a pure mathematical sense, that the infinity to minus infinity should be there. Like a lot of times with these things, when you're introducing something, it all sounds a little bit freaky, but hopefully a few examples will kind of make us see that this is really all pretty intuitive, I hope. So let's just do a few examples. So the first example, here's a PDF that's given to us. The first question is just to verify there is a PDF. I'm going to draw the thing. Actually, I like drawing graphs. I know students don't, but I do. So I'm going to draw the graph. I always draw one, even done asked for sometimes. I like it that much. But sometimes you could be asked to draw the graph of this. We can see this is just linear. It's going half x up like that. Now the thing is that let's go back to the idea I was saying about infinity. Let's label that fx. To this idea of infinity to minus infinity. Basically what happens is the value of this function only goes from 0 to 2. This it's only throwing out zeros to 2, whatever the distribution is. So any other values are impossible, apart from 0 to 2. This is skewed towards the right-hand side, by the way. It's a bit, there may be circumstances in which this happens. The mode is on the right-hand side. So in other words, it's much more common, it's much more likely to get numbers close to 2 than it is numbers close to 0. Of course, I wouldn't say exactly 2, because as I said before, that's impossible. But numbers close to 2 would be 0. We do, by the way, talk about the mode as being the highest point. So the mode is 2. So it's where the data is most concentrated, which is the highest point of the graph, which will be 2 in this case. Okay, because it's where it falls highest, the local maximum, if you like. But anyway, I digress. We'll talk about a mode a little bit later. So it says verify that it's a PDF. So I'm just drawing the thing here. That's the way, because I like drawing graphs, and for me, it's the easiest way of verifying it. Basically, we need to show the properties, the two properties of the three that we really need to make sure we show are satisfied here are that it's always greater than 0. Well, just drawing a graph of that's probably not good enough. I might also do a bit of might be good enough, but I want to be a bit more pure mathematical than that and say fx is equal to half x, which is greater than 0 since x is greater than 0. Let's put inclusive on there because it can be equal to 0. So so it's always positive. Oh no, I know it's got to be less than 2, but that's not the point. The x is always positive, and therefore fx, which is equal to just half times x, is always positive as well, and we can see it from the graph. Right, so that's the first. So that condition is satisfied. Then the other thing we need to check is true is that the area underneath this thing is equal to 1. That area is equal to 1. Well, we can see that this point here, fx. So we can just write f2 equals to half times 2 equals to 1. Okay, so I'll put that, let's annotate that there. That's equal to 1. So therefore the area equals to the area equals to, and we could integrate half x to between 2 and 0. You might prefer to do that, but I don't. So I think it's a sledgehammer to crack a nut. It's a triangle, so let's find the area of a triangle. Half times base times height, so it's half times 2 times 1 equals to 1. So the area equals to 1. So therefore this is a viable or possible PDF. Would be a bit odd if they gave you a question which wasn't, but there you go. This is a possible PDF. The exercise I'm going to give, I'm going to associate with this task, does involve some examples which are PDFs, and you've got to decide whether it is a PDF or not, and what you're looking at is whether these two conditions hold or not. Okay, so that's the first part of it. The second part of it is to find the probability that x is less than or equal to 1. I'm going to draw the diagram again. So we want the probability that x is greater than 1. We want that area. It's a trapezium. I might put it there, so we can work out that area, we can integrate. I might prefer to just say it's half of the, work this area out and take that away from 1 in this case, but so long as we find a way of working this area out, because I'd find the probability that what I'm effectively doing here, not the only way of doing it, we could just work out the area of a trapezium, but it just occurs to me it's easier to work out the area of the triangle. So we're doing 1 minus p, x is less than or equal to 1. So that's 1 minus, and we can see that this is a half base times 1 times height, which is a half. So that's 1 minus half, 1 minus a quarter, which is 3/4, which makes sense. So the area of that trapezium is 3/4, or I could have worked it directly from the trapezium, or I could have integrated. Again, just to reiterate again, I've kind of used an inclusive inequality there, and I've used a strict inequality there. It actually doesn't matter with continuous distributions. With discrete distributions, it matters hugely. So I've just done that for consistency. If it were a discrete distribution, I would have to change the type of inequality or be aware of the type of inequality I'm using, but not with continuous. Okay, so I've just done that for consistency there, not that it's actually important here. Okay, so let's do another example. Okay, well, for the students this is targeted to, have just done some work on functions and the modulus function, so I thought this might be a nice one to put in. It's a bit of an unlikely distribution in some ways, because it's kind of becoming less concentrated around the middle, which is a little bit unlikely, but it might be situations where that occurs. I'm going to draw a diagram for it, and there's only one question to this. Find a probability that this thing y is less than a third or greater than 4/3. I'm going to draw a diagram for it. It's a bit awkward with writing the y-axis on the horizontal, but never mind. So I might call this, let's call this fy, just write it, annotate it fy here. We've got y along here. And this is the modulus graph. Now the modulus graph, and it's only been defined between 0 and 2. Okay, so what happens is when y is equal to 0, we've got the modulus of that, and that's equal to 1. But when y is equal to 1, comes down to 0, so it's a little unlikely kind of distribution like this, but never mind. You never know. Can't think of any examples where that would model any particular data, but again, just thinking of this from a pure mathematical point of view, that's the distribution, one where the actual concentration is around the two ends, not in the middle. There's no strict mode here, because in fact there's an equal height on each side. So it's a bit unusual as well. But anyway, here we go. So we want to find the area, and we could integrate, but I'm not going to. we'll have plenty of chances to use integration in a moment. So we've got a third here, and that's one. That's a 1 here, so we want that area. And then greater than 4/3. Right, 4/3. That's going to be just a little bit. That's going to be there. Okay, and what we can do is we can say, right, this value here, putting a third into the function, that would be 2/3 here. Yeah, that would be 2/3, because a third take away 1 is minus 2/3, modulated is 2/3. And this value here for 4/3 is 4/3 minus 1, which is 1/3. So that's 1/3 here. So we want the area of these two bits added up together. Okay, we want the area of this, so I forgot to, we need to say the whole lot of that. We want that area, which is the area underneath this modulus function from 1 to 1/3, and we want that area. So we can say that the probability that y goes between 1/3 and 4/3 equals to the area of this triangle, which is half base times height. Half times that length there is 2/3, times by the height, which is also 2/3, plus the area of this triangle here. Now this base is 1/3, so it's half times 1/3, and the height is also 1/3. So this bit here is equal to 2/9, and this bit here is equal to 1/18. Adding those two together, that's 4, that bit would be 4/18, so that's 5/18 is the probability that it lies between those two values. Okay, let's do another example. Okay, so question 3. This is quite a common thing that they ask actually in exam questions. They kind of put a value of k in, and they get you to work it out using the conditions of PDF, and in particular the area underneath is equal to 1. So let's just say here, because again, remember theoretically our thing is infinity to minus infinity, but we only, between any values apart from 1 or 3, we're 0. So for all intents and purposes, all we've got to use is the fact that the integral of 3 to 1 of kx squared dx equals to 1. Okay. Now I could bring up the calculator function, because you could easily use the integrating function on your calculator, but in this case it seems quick enough to actually just integrate it. So we've got k x squared integrated is x cubed over 3 between 3 and 1 equals 1. So k, that's 27 over 3 minus 1 over 3 equals to 1. So we've got 26 over 3, k equals to 1. So that gives us k equals to 3 over 26. Okay, so you're going to see that type of thing, maybe a little bit more complicated than that, but using that principle quite a lot. Then we find the probability that x is less than 2. Did I mean that? Yes, I did. So probability that it's less than 2. So there we're basically integrating between 2 and 1 with our value of k, because we now know that fx, we've got a value of 3 out of 26 there. So all we're doing there is probability x is less than 2 is equal to the integral of fx, which is 3 over 26 from 2 to 1 dx, 3 over 26 x squared dx. And this time I might use the probability thing on my calculator because of the 3/26. So here we go. So don't forget, you can use it unless it says detailed reason, or it's clear that, or it says so exact, or that there will be circumstances at which you can't use your calculator because of the wording of the question, or because you required an exact answer and the calculator doesn't give you an exact answer. So you can't certainly use this for everything, but certainly here we can use a calculator because it just says find. So we can, let's just write the function in. The value of k is 3/26. And we need to press the alpha button, alpha x, and then make sure we got the squared in. And that should give us the probability that we were looking for. 7/26. So there we go, we're done. 7/26. Okay, remember, one of the things that happened in the exam in 2019 for OCRA is a lot of students wasted time working things out. I mean, you could say I did it a little bit here, but I just wanted to at that stage because it's quick. But really, I even wasted a little bit of time there. I could easily have just keyed this into the calculator. Well, I wouldn't have had the k, so I could have keyed the integral of x squared between 2 and 1 into calculator and done it. But there will be plenty of times, don't worry, the way they word the questions, where you really can't use the integration function on the calculator. But when you can, you should. And we can here, so we did. Okay, so that's that question done now. Question 4, this which will be our last example, and hopefully you'll go away thinking you know a little bit about probability density functions before we continue with normal distribution. So one more question to go. Okay, sorry about the sort of different kind of colours of writing there. Don't know why that's happened. Right, so okay, so here I've tried to think of a particular example. Maybe a particular species of frog is modelled by this in grams, the weight in grams, but a particular species of frog varies between 20 grams and 30 grams, and you've got this kind of quadratic function which is being used as a model for it. But again, we've got to find the value of k. So we're going to use the fact that integral, let's make this, just annotate this up properly. Solution, so for number it properly as well, a, b, c. So solution for a, we're using the fact that the integral of the value of a PGF between infinity and minus infinity equals 1, but infinity, there are only values between 30 and 20. So we're going to use the fact that the integral of minus k x minus 20 to x minus 30 dx from 30 to 20 equals to 1, and I'm going to use the integration. In fact, let's just take the k out of this. Bit awkward there anyway. X minus 20 x minus 30 dx from 30 to 20 equals 1. I'm going to bring up the calculator again now. Okay, so the calculator, let's bring it up again. Right, so the calculator, I obviously just want to do that bit without this bit here. I want to key into the calculator. Apologies, it keeps disappearing. So let's go to integration sign again. The integral, the limits are 30 to 20, using the arrow keys to use the integral thing. Then let's key it in. I'm using the arrow keys not particularly effectively here. Don't know what's happening. Eventually I'll get there. Okay, got there by fiddling around, not quite sure what's going wrong there, but anyway, we got there using the arrow keys to bring it down. I might as well don't multiply out, when you don't have to. We can just key in the brackets. What if you make a mistake? I've made mistakes with multiplying out brackets plenty of times before, so just key in the thing as it is. There we go. X minus 20, x minus 30, that equal, and we're expecting a negative answer hopefully. So that gives us minus 500 over 3. Brilliant. So we've got minus k times minus 500 over 3 equals 1. So that gives us k is equal to 3 over 500. Okay, brilliant. So going to part B was to sketch the PDF, and I note it's a upside down or quadratic going in with negative value of a at the front because of the minus sign at the front. Also note that it must go between 20 and 30 because when x is equal to 20, fx is 0, and when fx is equal to 30, because x minus 30 is equal to 0, that's equal to 0 too. So the graph, and let's draw the whole, or at least emphasize the fact that it's 0 for values between, which are not between 20 and 30. It does that. And like that, where this is 20 and this is 30. Let's label that fx and this x. Okay, so that's a sketch of your PDF. And the next bit is about the mode, but before we do the final bit of that question, just to say I didn't leave a part on this, but this is going to give us, probabilities. So if we wanted to find, for example, a probability that x lied between, 22 and 23, we'd just integrate from 23 to 22 of, now we know the value of k is 3 over 500, x minus 20, x minus 30 dx, and then we would then we could work that out using the calculator or whatever, and that will give us a probability that x lies between 22 and 23. Okay, just wanted to put that in. It gives us probabilities, folks, and the total area underneath it has to be equal to 1. So it's all, I hope that this is you're getting the idea of this, and it's fairly intuitive now. And you'll see different types of functions in the assignment you're going to do on this. You'll see different types of functions and different kinds of models, but they all have the same thing in common. The area underneath's got to be equal to 1. And it's always got to be positive, which makes it a reasonable model so that you can, when you integrate underneath, you work out possible probabilities for this random variable. Anyway, the mode, as I mentioned before, going way back to the first question, the mode here was 2 because that's where the highest point was. Okay, it's impossible to actually be equal to 2, or theoretically impossible because it's continuous data. But the data is more concentrated around the end there, where x is 2, the mode is 2, more pure mathematically, it's the highest point or the local maximum of the graph within the range of appropriate values. Now in this case, we don't need to differentiate. In other cases you might, if you ended up with a cubic or whatever, so say you ended up with a kind of skewed distribution with it, which might be defined by a cubic like that, say. Then you would integrate. You'd have to differentiate, but not here. The mode clearly is equal to 25. Mode is equal to 25 by symmetry. Okay, so that's nearly it. That's a good place to stop. Any questions, please ask. And we will be moving on to a normal distribution. This is where the actual PDF is incredibly complicated, so we'll be using a calculator to work out probabilities largely with that as well before doing some more in-depth questions. Okay, cheerio.